Hello, everyone. My name is Charles Rice. I actually now work in the customer support team, and our agenda, pretty short actually. I'm going to focus on three things. The measurements validation worksheet, just because no one ever really talks about it, and probably even less people use it. But I think it does have some useful functions and features that I would just like to highlight. And then we'll spend most of our time on modal synthesis worksheet and modal validation worksheet. Those are two worksheets that open up anytime you open any of the modal analysis packages, Polymax or just regular modal analysis using the TimeMD curve fitter. So why don't we just jump right in, and I'm going to switch over to TestLab here. Now the validate worksheet, you're going to find this in the context of what we're talking about. If you're doing impact testing, you would find this validate sheet here. I opened MIMO FRF testing. You also will find the validate sheet there. And really what it is at the end of your measurement campaign, it's an opportunity to look at the data again from an overview. No doubt, as you're acquiring the data, you're being very careful, studying your measurements at each average, looking at the coherence as they're coming in. But over a long test, some tests take a couple days, moving shakers around, things like that. You may not have a good overview of everything at that point. And as soon as you come in, you'll see that it displays all the runs in the section that you're in, but you could go to a specific run. And the idea being you want to look at all the runs at the same time. And any of the data that you measured would be in this function type that you would select. If you measure the coherence, then that would be in the dropdown. If you didn't measure the coherence, but just the FRF, I don't know why anybody would do that, it wouldn't be in the list. Or if you measured the dynamic stiffness, that would be in the list that you could choose. And kind of as you imagine, similar to modal data selection, you can basically, if you want, click on different points and take a look at the FRF. Now, we're looking at two references here as well. You could look at just one, or you could look at them both. Yeah, one nice thing about this as well is that we have at the bottom here is display on geometry. So if I click this on, and I have my data type right now set to FRF. If I come down here, I can say, hey, show me all the measured points. And you can see this turquoise-ish, bluish green, I guess, aqua green, I don't know what color that is. These are all the points that I did measure. This point right here, I don't know if you see it says NLG slave. It wasn't a point that had any data, it's just a slave point. So I wouldn't expect it to have any data associated with it. But this is just if, maybe you're doing a roving hammer test, you're going around a big structure. At the end, it's just a quick way to make sure, hey, I have data for all the points in my geometry. Something else you could look at, reference points. So on this plane, there was a shaker here and a shaker on this wing. So the right wing at the tip and the left wing at the tip. So if you didn't have knowledge of this, I guess it'd be apparent to you. Something else you could do, you can also go to FRF coherence. Just wanted to show this. And what you could do, you have a couple options. You could just look at the Bode by itself or Bode front back. But if you just choose front back, what you'll see is you have the FRF data and coherence on the same plot, which might be useful if you want to look at why do I have a dip in my coherence? Is it lining up with one of the peaks I have in my FRF? So something simple and small, but just wanted to point out you have some flexibility in the display. And as always, you can bring in other data and drop it into this front and back if you wanted to compare to some other tests that you have data with, or put some type of maybe an FRF from C or something to see if you were capturing all the modes that you were expecting. That's available to you. One last thing I kind of wanted to highlight on this validate worksheet, if we go to function type coherence, I think this is kind of neat. If we go back down to display on geometry, I can say coherence values. And you can see points. So as you might recall, our reference, our shaker or input to the system was at the tips of the wings. And right here, I have a color scale of my coherence. I have it set 0.75 to 1. Usually we like to be at 1, but maybe depending on what you're testing, how easy it is to excite, or far away the points are, your coherence is going to drop, but you maybe would like to keep it about 0.7, the worst, or something, 0.75. So that's the scale I have set. And as you can see, points that are closer to the inputs, I have very high coherence, makes a lot of sense. Points that are a little further away, coherence is lower along the fuselage of this plane. So it's just a visual overview of the coherence. And you can select the band over which the coherence should be calculated. You can see this double cursor here moving around. So it's kind of a cool feature to kind of get an idea, well, maybe I should think about testing again and maybe having another shaker out on here on these fins. Something to consider before you even start going through your modal analysis process. So that's the validate worksheet. Like I said, you'll find it in the acquisition products like impact testing, MIMO, FRF testing. So I'll just shut this down. So we're going to move on now to the modal synthesis worksheet. And we'll go back into Test Lab. And I just have the desktop open here. And let me see what section I want to be in, Demo 2. Now, if we go over to Polymax, first thing we come up with is we have to set our band. Normally, what you want to do is choose a valley for the end of the band. Like, you don't really want to stop really close to one of the peaks in the sum. So always try to choose to be in the valley when you're making your analysis band, and we'll just leave it here. It's good enough. In fact, another thing too, because we have so many references, I'll just turn this on. Instead of some people might like looking at one of the mode indicator functions. This is the multivariate mode indicator function, and what it'll do is it'll drop down everywhere where it expects to find a mode. Now, I probably like the complex mode indicator function a little bit more. One thing that's different about the mode indicator function, if we go to the complex MEF, is, well, I guess it's true for them all actually too. You need to tell it to use the other references. The number of mode indicator functions that you can have is equal to the number of references. So maybe we'll do this just to give it a little bit more interesting view. Typically, I would probably just use 2. You don't get a ton more value for having 4 in this scenario, and it's using a singular value decomposition basically to find if there are 2 modes versus 1 mode at any particular frequency point, the number of singular values that it finds at each frequency line. Now, as you saw, we're measuring with this data a disk, so it's symmetric, so you have a lot of repeated roots, closely spaced modes. So that's why you're seeing at a lot of these points, you see 2, you see 2 here, you see 2 here, you 2 here, 2 here. It's because of the symmetry and what we're measuring. So you have your options there. Coming over to the stabilization diagram, one thing I like to always turn on, you just make sure it's on if you don't ever use it, but it's this automatic modal parameter selection tool, and does exactly what you think. Selects poles for you. Now still there is, I guess, the standard warning that we still need to investigate the data ourselves and make sure the selections that it selects make sense for our particular case. But it is a very robust tool. I usually start here and then I might go in and look at each one of the selections, zooming in, just drag and drop around the zoom. And if you have something that has high modal density and it's not selecting multiple poles that are close to each other, you could just go in and select it yourself, or you could change this modal density slide bar, and then it would do a better job at selecting additional poles that are closely spaced in high modal density situations. So just wanted to touch on that. So we've used AMP's automatic modal pole selection to select our modes, and we'll just go with what it selected. Now we want to calculate our shapes. I always like to start off with complex, and complex versus real. A real mode, a normal mode, all of the points are going to be moving in phase or out of phase. Whereas complex, that may not be the case. They're going to have different phase relationships. But if you choose complex and something has nothing but real modes, it's still going to look like a real mode. Whereas if you choose real and there's some complexity there, it's going to force it to be a real mode. And that might be a wrong assumption. I like to start off with complex. Always use the lower and upper residuals. Basically, we're just accounting for the effects of the modes that are not in that band that we selected. We selected the band that we're going to do our modal analysis over. Well, there are other modes, you saw them, right, that passed there that we didn't have in our band. They're going to have an effect on those modes in the band. So we want to be able to account for that. So we always include lower and upper residuals. And if you don't use this, when you're trying to do the modal synthesis next, you'll see it'll really affect the results a lot. Why don't we just do the date? You calculate, probably very familiar with this. You can drag your modes over and then just step through. Like I said, you can look at it and it looks like a very real mode. And it's what I expected. It's what I expect for this structure. All right, now we're going to finally get to the worksheets that really are our focus today. We'll start off with modal synthesis. So this is the modal synthesis worksheet, and maybe we should first start off with getting a little familiar with the display layout. So we have 4 displays, and you can control the number of displays using this drop down menu here. We have 4 because we have 4 references. By default, you'll have the number of displays as references typically, but you could set it to 6. Of course, these 2 would be empty, but if I did want to rearrange how it's displayed, I could just choose 6 FRFs to display. But I prefer the 4 references, 4 displays. So we'll go back there. We see the output and input DOF IDs, and then probably most importantly on the sheet, we see the correlation and the error. So the correlation being related to more how our synthesized FRF matches our actually measured FRF. As you can see here from this legend, the synthesized FRF is the green curve. That's the one we are calculating based off our curve fitting process, the frequencies, the damping, and the mode shapes that we calculated. We use that information to calculate now this synthesized FRF, and we compare it to our actual measured FRF in this modal synthesis process. This error represents how closely the amplitudes match. So we can see here for definitely these 4, very good correlation, 99%. And error less than 1% for the 4. And if you wanted to review the other ones, you could just step down using the navigation controls here, but probably more efficient for your time. You could use this play button. You can even select the speed, how fast you want it to basically scroll through. So we'll just crank it all the way up and step down. So plays groups of 4 till it gets through all of our response points. Okay, and of course if you wanted to play going to the right, you could just choose the first FRF in that first column for disk 1 and just hit the play. Something else important to know here, make sure you have the lower and upper residual turned on. That'll have a strong influence on the calculation of our synthesized FRF. For example, if I turn it off here, you can see the influence of the synthesized FRF, so you want to have that turned on. So with regard to reviewing the data again, what we could do if we wanted to get a chart of all of the error and correlations, we could play through the data and generate actually a correlation and error list at the end. Turn it on, you go to synthesis parameters, you make sure generate correlation error list is checked on, and go to the top of your matrix of data and just simply hit the play button down. Speeds through. And then when it's done, it's going to pop up a correlation and error list for us of all our points. And what we could do here is, well, you can sort it, ascending or descending. So you can see our largest error is less than 3%. So pretty good fit to this data. Something else you could do Right now we're comparing our modal model to the FRFs that we measured, and the ones that we use in the curve fitting process. But we could choose another set of FRFs to compare to just by selecting them using the change. Additionally, the synthesized FRF, you can choose to build up a table of points that you did measure. Now that we have this modal model, we can build up a full FRF matrix, a 48 by 48. So right now these are our 48 output points and our 4 input points. But what we could do, move those over and just select everything again, put those here, hit OK, close, and if you see here, now what we have is a full 48 by 48 FRF matrix. So you can use these synthesized FRFs here for other processing work. Even the points that you didn't measure, once you have an accurate modal model, you can synthesize those points to get a full matrix. I think primarily that's what I wanted to show. You can also here, with the synthesized FRF, you can use the frequency information from the FRFs in our modal processing, but you could also choose the start frequency, frequency resolution, or frequency step, number of lines. So if I wanted to change it to 2 Hertz, for example, and maybe change this frequency lines to, let's just say 2000, you can see our synthesized FRF updates. We can change the bandwidth and the frequency resolution of those synthesized FRFs that we're using. Okay, I think that's it for what I really wanted to show. So moving on to our modal validation tab. So when we come here, typically one of the first things we might check is we might look at the MAC or the auto MAC. So we'll hit, this is our processing set that we calculated. We'll hit auto MAC, and you'll see you have the list of modes here on the right and the same list of modes across the top. And what we're doing is comparing mode 1 to mode 1 here, mode 1 to mode 2. And just in case you're not familiar with the MAC, it stands for Modal Assurance Criteria. And it basically allows us to determine how similar 2 mode shapes are. And think about them as snowflakes. The mode shape at one frequency should be different than a mode shape at another frequency. Should be unique in that sense. So when we're doing this auto MAC and we're comparing a mode set to itself, what we would expect to see is across the diagonal, when we're comparing one mode to itself, 1 to 1 or 2 to 2, 3 to 3, it should be 100%. And everywhere else, it should be 0. That would be our expectation. Sometimes it's easier to, if you go to this drop down here, table of geometry, to look at it at the matrix geometry view. It's kind of the one I appreciate the most. And you can click and drag and move this around to get the angle you like, but I prefer the views top as the best, I guess, easiest way to look at it. Using the middle scroll button on your mouse, you can kind of zoom in and out. And I was saying, we would expect high values along this diagonal where we're comparing a mode to itself. And oftentimes, that's what we do with the MAC. We're either going to compare a mode set to itself and do what we call an auto MAC, or we'll do a MAC comparison between our test modes and maybe our CAE modes. Or maybe we use 2 different estimation methods and we'll compare those. For example, if we calculated complex modes and real modes, we may want to do a MAC comparison between those 2 to see how good of an assumption that is. And looking at these results, we can see in general, all of our off diagonals are pretty low, with the exception maybe of these 2 points. Modes 15 and 8 and 9 and 16. And this could be related to something that the auto MAC can tell you. As you can see, we're getting higher in frequency down here. If you do not have enough points, sensors on your structure, and you do your test, you may not have enough resolution, spatial resolution, to say one mode is very different from the other because you're not measuring enough points, and the shape as you go higher in frequency typically gets a little bit more complex. So if you don't have enough points, then you may have these high values in your MAC. So maybe adding a few sensors could knock these down. So that's one thing that the auto MAC can tell you. Another thing we might check with our mode set after looking at the AutoMac is the complexity. So I'll just hit complexity and you see nothing popped up. Well, you need to be in the table view. And to talk about this a little bit more, I actually have some slides that will work through to understand what each one of these metrics are: the MOV, the mass sensitivity, MPC, MPD, scatter, MP. So we'll talk about what all those mean. Let me bring up my slides. Okay, here's the first slide. So let's talk about the MOV first, mode over complexity. And just to summarize it here, I don't want to really read the slide to you, but this criteria is based on the idea that for a mechanical structure, when we add mass to it, at a certain point, there's expectation that the natural frequencies of all modes will shift downwards. So that's what this criteria basically is evaluating for the mode shape vectors. And it's a percentage. And we should, for high quality modal result, see a near 100%. If we have a low MOV value, that can indicate perhaps a noisy measurement, or maybe we have a computational mode. It's not a real physical mode of our system because it didn't shift down when we added mass. And could also be related to our estimation process, maybe some error in how the data was analyzed. Next would be mass sensitivity, kind of the same idea. This metric checks the sensitivity of a mode frequency for mass change and makes it a little bit simpler, the minus sign or a plus sign. As with the MOV, similarly here, when we add mass, we would expect frequency to shift down, and that's what the negative sign represents, a shift in the resonant frequency down. If you have a reference, and perhaps if you had noticed here, we have all our modes in our mode set, and across the top we have each of our 4 references for each of the metrics. Now, if you hadn't noticed, some of these are not minuses, right? So what does that mean? Well, if it's just 1 or 2, perhaps it's just not a well-excited mode by this particular reference. If you see a lot of them in this column, then that probably means the reference is not in the correct direction. And I'll show you an example of both of these when we go back to test lab. Next, we have the MPC, modal phase collinearity. And this checks the degree of complexity of a mode. And what we're looking for here is a value near 100% if it's a real mode. And if you have a low MPC, indicates it's a rather complex mode. And that complexity could maybe be due to local damping, maybe even errors in the testing method or mistakes in analyzing the data. But we're looking for real modes, 100%. And if it's not, if it's a lower value, typically it's a complex mode. MPD, mean phase deviations. All 3 of these, we can kind of group these into how complex a mode is. That's what we're looking at right here. And this is another complexity indicator. And what we're looking for a value is near 0 for real modes, or we could say normal mode, same thing. But if it's a higher value, then that indicates more complexity. And the scatter is really an evaluation of the MPC and MPD. And it's either going to be ranked as high, low, or a question mark, meaning it's not possible to say definitively one way or the other based off of the results. This table is actually found in the help. I just pasted it here for your convenience. But if you look through the data here that I have highlighted at the top, we can see a lot of them are low, a few of them are high. So what does that mean? We have for the low evaluation, we have MPC of greater than 90%. Which is what we would expect, a higher number for a real or normal mode. And an MPD, that mean phase deviation less than 15%. Also, we expect a low number here for a normal or real mode. So that's what that's telling us. Now, when it's greater than 90% for MPC and for MPD, it's greater than 15%, we have a question mark. No evaluation is made there. Likewise, when the MPC is less than 90%, and the MPD is less than 15 degrees, also we have a question mark. But we can make an evaluation when we have high scatter or a complex mode, when we have less than 90% and greater than 15 degrees. Now this last one, MP, stands for mode participation. And here we're looking for a value for a well-excited mode near 100%. And we're saying that this mode is well excited. For example, this 20 reference excites this mode very well. with that 100%. So when we say a high value, it means that particular reference is exciting that mode very well. One interesting thing too, when you look at this last column, the MP percentage, if you add up all of these values here in this last column, it's gonna be 100%. So when we look at the values in the column, in this case, maybe the values of 10 and above, it would be considered as dominant modes or important modes in the mode set. A good way to evaluate the importance of a mode, looking at this MP percentage. Okay, let's go back to Test Lab. One other point I want to make quickly before we get through a couple more things before we finish up is if we hit this advanced button, we can see here we can turn on and off what metrics we see in that complexity table. We also have the option to look at full or compact information. You might recall that a lot of the information in the compact view was based on reference, whereas in the full view you get information per response, so that could be helpful as well. So we'll hit OK. Additionally, you might recall that I said we can do a MAC evaluation of a mode set to itself. That's called an auto MAC using this button. But we also could do the MAC to another set of modes. Maybe they came from CAE, maybe they came from analysis with a different estimation method. For example, the mode set we've been looking at was calculated with a complex residue, but I also calculated one here with that same data using a real residue. So we could look at a comparison between those two. So why don't we do that? So we'll hit the MAC button and we'll need to go to the matrix view. So we'll go matrix geometry. And now we see we have a mode set A, which is this first one, the complex, versus processing B, which is this one here, which is our real modes. We can see there's very good correlation between the two. So the assumption of a real mode would be appropriate if you didn't want to use the complex calculation, and maybe you would do that because you're going to be sharing the results with some of your CAE team members and they typically would need you to give them normal modes. Something else I want to show you here, we can use this compare button. So after we hit the compare button, we'll need to go to a table view, go table geometry. As you'll see, it's a comparison between processing A and processing B and things you could compare with your different mode sets, differences in frequency, differences in damping, MPC, MPC of A and B, and also MAC percentage. Okay, I think that's pretty much mostly what I wanted to show. Maybe just a couple quick points in closing. There's a couple items here that we didn't really touch on. There's this normalize button. So if you did calculate a complex mode and you wanted to normalize it, you could do that right here. There's two methods, amplitude and quadrature. And also you can scale your modes. So for example, maybe a unity length or unity component people would use to scale one of their modes because they're going to maybe make a tune mass damper, and they would want to find out what that modal mass was so that they can maybe choose 10% of that value. So they would scale it first and then come grab that modal mass number. So you can do all of the scaling of your modes here as well. Well, I think that's all I really wanted to share today. Maybe I'll switch back to my slides real quick. I'm done and just wanted to say thank you.